Last time we were talking about case 2 regarding the solution of the kinematic wave model. So let's remember in case 2 is the acceleration case. So upstream we have a larger density. There's going to be state U, and then state D is downstream density. Okay, and as usual we draw the wave speeds and we call them W's, right? So to deal with the discontinuity in the Riemann initial conditions, we do this smoothing approximation, right? And for each point in the smooth function, we find the corresponding wave speed, and then we draw those characteristics, right? Like W1 right here. W1 would be one very close to WU. Yeah. All right, so that's the previous lecture. And then we make epsilon tend to 0 so that we recover the discontinuity there. And the final solution can be just expressed as this time space diagram, simply with WD right here and WU. And those represent the boundaries of states U and D, and then in the middle here we're going to have a fan with the wave speeds given by all the wave speeds between WU and WD, right? So this is what you get when you solve this in the computer. So what you see here are the trajectories going up, right? So I could put arrows, if you will. But the other straight lines, the fan, those are the characteristics. So I wanted to show you how the trajectories look like when you have a rarefaction fan. So again, this is going to be the state upstream, right, and downstream in red and purple. So here you're going at a slower speed, VU, and then you're going to accelerate to the speed at state D. Okay, but the problem is that the acceleration is very slow. So as any trajectory touches a characteristic, right, for example here, the slope of that trajectory at that characteristic is the slope of the waves, the slope of the cars at that wave speed. What I mean by that is, for example, here, remember, in state U, the speed of vehicles is Vd, and the characteristic is Wd, right there. And same for state U, right? So that's Vu. So every time you touch a characteristic with the trajectory, such as this one right here, the speed at that point is going to be the speed of vehicles at that trajectory. Let me say I in this case for the ith characteristic, which could be somewhere here. Yes. Wi. Alright, so Wi is the speed of this characteristic right there, and Vi is the speed of cars when they touch that characteristic. Okay? So that's what we're doing here. And that's how we could calculate these trajectories. Now, the point I want to make here is that the speed of vehicles is really gradual inside the fan. Okay, so, and remember, inside any one of these characteristics, the speed is going to be the same. So let's take that one. The speed of all vehicles crossing that characteristic is going to be the same, equal to Vi before, right? So if you take the first few trajectories, they accelerate reasonably fast, so it only takes, a couple of, let's say, seconds to accelerate from VU to VD. But if you take this one, it takes much longer time to accelerate. So let's follow this trajectory up to here. So that time is greater. And if you keep going through the platoon, the last vehicle will have a longer time to accelerate. Okay, and that we do not see in practice. In practice, we tend not to see these rarefaction paths. So let's see real vehicle trajectories. So this is the trajectory explorer, remember? Here you see typical trajectories accelerating, such as in the case that we're talking about. So you see that, for example, I could draw a line here, and that's the line where vehicles go from upstream density, in this case it's jam density almost, towards the other density. Right, we could see what the states are here if I go in platoon mode, right? Let me do it right here. Yeah. So here you see that. Yeah, now you see it. So you see that this would be the upstream and downstream traffic state in this case, actually. But let's just focus on the acceleration process, right? Because here we have kind of the two solutions together. But if you start with the acceleration process, we start from a congested traffic state right here, right? And we accelerate to this more free flow traffic state up here. Okay, and you see that it happens on a straight line, and we don't see the rarefaction, and that's the point we're making here. We'll go back to line mode. Right, a rarefaction would be a zone in the time space, kind of like that you would see a cone of some sort, maybe like that. Okay, right, such as this one, right? So we see a cone very clearly, but in practice we don't see such cones because what we tend to see, it's an area of acceleration. So people take the same time to accelerate from VU to VT in the figure before, independent of their position in the platoon. Right? And it's again because we don't see these spans. All we see is kind of a sharp transition between, in this case, jump density and the free flow traffic state downstream, or less congested. Okay, so that's the point about rarefaction plants. Now, it's not a waste of time because it turns out that when the triangular diagram is the one that you choose, then this is what happens. Okay, so we have the same idea, right? We smooth out the initial conditions and we apply the transport solution. But when we have a triangle as a diagram, so, okay, so that's going to be state C, the capacity. All right, so you start, again, you can start here upstream and then you go little by little, right, in the smooth part of the initial conditions. And then you would see that all the wave speeds in all these points are all equal to negative W. Right, so WU here is just negative W. Okay, for all these, right, for all these characteristics, they all have the same wave speed because it's a straight line. And then when you reach the capacity state, let me prolong this line. When you reach the capacity state right here, is as if you had all possible wave speed concentrated at one point. And that's kind of the fan that appears, right? Because once you reach capacity, right, the last wave speed was negative W, then at that point you have all wave speeds from negative W all the way to positive U, which, so this should be U. The slope of all the characteristic downstream of that point. right? Yeah, and the point of where all that happens is the critical density right over here, right? Okay, so what happens is, oops, sorry about that. What did I do? Okay. What happens is that at this point you have all these characteristics, and all they carry the same flow in traffic state C. So all these guys in red right here, they all propagate or contain the same traffic state, which is the capacity state. Okay, so the fan exists. You can see it right there, right? It looks like the same fan, but the difference is that before, all those red lines carried a different traffic flow, a different traffic state. But in the special case of a triangle, all those different traffic states collapse to the tip of the triangle, which makes it such that they all carry the same flow. Okay? And therefore, the, if you will, the solution in the time space, the abbreviated solution in the case of a triangle diagram is simply U, D, and C in the middle. Okay? We don't need to show the fan because it's a very special fan where everything is capacity. So that's going to be the abbreviated solution for case 2. And these are always negative W, and this is U. Okay, and if you compare to the other solution, right, here it was your WD and then W2. No, WU. Right, but all these characteristics carry different flow if you have a concave diagram like this one. All right, so let's recap real quick. It turns out that this what we did, we call the entropy solution of case 2. Because it turns out that case 2 has infinite solutions or multiple solutions. Now, it turns out that you could apply the shock solution and it would also be a solution to this model. Actually, you could, in the fan here, you could put almost anything. Well, not zero, but anything between U and D with a shock would be a solution that satisfies the equation. Now, what happens is that those solutions are all non-physical. People don't drive like that. Okay? The way people drive is that we want to get to a destination faster. So the entropy condition says, and this is how we define it in the case of traffic, we select of all those multiple solutions the one that maximizes the flow at all points in space. Okay? And that turns out to be the vanishing viscosity solution that we've been talking about. Right? The one where the discontinuity, we smooth it out and then apply the transport solution and then make epsilon go to 0. That's the vanishing viscosity. But it is a consequence of this entropy solution, which the only reason we use it is because we need to select one solution of the many multiple solutions that there exists. And the way to select it is using this vanishing viscosity method. Okay. So, yeah, this is again the simplified solution with a triangular diagram. So this means triangular fundamental diagram. And these are in red are some trajectories. So again, in state U, you're driving at VU, which you get from here. And then once you pass this wave speed, which is negative W, then you're in state C instantaneously. Okay? And this highlights kind of a shortcoming of the model, which is that all accelerations are infinite, or decelerations, okay? So we haven't put in the linear model for accelerating yet. And this is one of the shortcomings, right? Because it assumes that as soon as you cross the shock or the wave here, you would change speeds from VU to the free flow speed. Free flow speed U, which is the speed at VC, right? So VC and U are the same here. All right, so solutions with triangular diagram are much simpler than the other solutions. But that's a good thing, because in this case, simplicity is a lot closer to reality than non-simplicity, like you see here, okay? All right. So now we're going to do a bunch of examples. In all these examples, we're going to have a multi-lane freeway, all right, with n lanes, all right, n identical lanes. They all obey a triangular diagram to make things simple. All right, and defined by the usual free flow speed U, wave speed W, and density for one lane, kappa. This capacity would therefore be given by this formula, but it's the same type of nomenclature we've been using so far. Okay, so in this example, we have an incident that happens on a n-lane freeway at location x1. Now it blocks only one lane, okay? I'm gonna correct that. So it's only one lane from t equals t naught to t equals t1. All right, and we need to describe what happens. Okay, so first of all, let's compute the capacity of the freeway with the incident, okay? So remember we said before the capacity was the tip of the triangle, right? That's Q right here. On a K cube lane. So that's for all lanes, right? So, I'm sorry, that's for one lane. The capacity for one lane is this one. So the tip of the triangle would be NQ right there. So if you block one lane, then like here, right? We have NQ is the capacity, and then QB, it's the capacity of the bottleneck, okay? And then in this assumption, it blocks one lane, so QB is n minus 1 times Q, right? Now it blocks two lanes, it's going to be n minus 2, etc. So yeah, it could have been two lanes actually, but typically it's one lane. All right, so what we need to do now is try to see at each time if we have a type 1 or type 2 problem. All right, so it's not said here, but the initial conditions is state A. Okay? So that's the state of the freeway before the incident and during the incident, right? So A is everywhere. So in part B here, where you see white, it's all traffic state A, okay? All right. So now we start with the first point right here. So that's when the incident begins, right? So at that time, you have a one lane that drops, and therefore the capacity drops to QE. So what happens is that two states are possible, right? One is in free flow and state D, and the other one is in congestion state U, okay? So when the bottleneck is active, which means that downstream there's free flow and upstream there's a queue, right? These are the traffic states that we're going to see. So downstream of the bottleneck is state D, and upstream is state U. That's an active bottleneck. If it's not active, it means that the the flow, the traffic state A, the flow of A is less than the capacity. So everybody can still make it without delay. So that's when A would be, below this line. But to make it interesting, of course, we need congestion, so A is above the line, so there's going to be a queue. And this is the queue that forms. Now, if you want to see the Riemann problems, what I suggest is you can draw a line here, really close to the origin. Okay, so and there's three traffic states, right? D, U, and A. So let's see, like zoom in versions of that. So start with A and U, right? So we see A and then we see U in this figure. And then we know that they have to be separated, either by a fan or something, right? So there's something in between. And then you ask the question, is this case 1 or case 2? Right? Case 1, remember, is the deceleration. So the upstream density, K ups, not to be confused with KU today. So it's going to be less than the density downstream, K downstream. And then case 2 is the opposite. Okay? Greater. So if you draw this, you see clearly that we're in case 2 because the density upstream is Ka and downstream is Ku here, which is case 1 right there. So the solution is a shock. And the shock is shown here between A and U, so the speed VAU is the one that goes right there. Okay, now we're going to do the same for U and D, if you want to see what the Riemann problems are. Alright, so you can draw the same parallel line here, but now we have U and then you have D downstream. And then in the middle, we don't know what's going to happen, right? We don't know if it's a shock or a fan. Okay, so upstream is denser than downstream, so it's a fan, right? It's an acceleration fan. Now, but this is a little different in this case because here we have a bottleneck, right? Upstream we have a different fundamental diagram than downstream. Or should I say, right at the bottleneck we have a maximum capacity constraint, right, given by this line right here. So we need to take it into account. So typically, right, from U to D, it's an acceleration fan, so you would want to do the solution with the capacity C state, right? But here, since we have the bottleneck, there's no capacity C, right? Because if you will, the way to think about it is that right at X naught, so where the incident happens, the fundamental diagram has this shape of a trapezoid. Okay, so you could apply the solution, case 2 solution to the trapezoid, and you would see, right, that you would start from QU, okay, and then you would move as we did in deriving the case 2 solution, right, along the fundamental diagram until you reach the downstream. So, and you see here that something similar happens in that all the densities here, they all have the same wave speed, which is 0 in this case, right, the slope of this line. So that's why we have this transition, right, that it's at the location of the incident, which is as expected. Okay, so this is another special rarefaction fan that collapses to a single value, a single line in this case. Okay, so in this case the solution is just a line, horizontal line between D and U. Okay, and then we reach time U right here. Oh, hold on. We forgot one. Yeah, there were four. Right, there's one that goes from D to A, right? Because we said everything that's white is A. So from D to A, you can always draw the same thing, right? But we have it right here. So D is upstream, and it has a lower density, right? So now KD is upstream, and KA is downstream. So KD is less than KA, right? So it's gonna be again a shock solution, right? Downstream density is larger. So the transition between D and A is going to be the shock solution. So you draw a line and see what the slope is. But in this case, since they're both in the free flow branch, which is linear, so the transition is going to be free flow speed U. Right? All right, and then we reach point U right here with time t1. The incident is removed. Okay? So now the fundamental diagram goes back to being the triangle. And then we do the same thing. You start here, so the density upstream is Ku, right? And then again, you could go a little bit farther here. Now, we already know that when you remove a bottleneck, right, it's like you give the green light. So there was a congestion state U. Obviously, what's going to happen is downstream, we're going to have a traffic state that is not as dense, right? And we already know that it's capacity. Okay? But in any case, you could start at case U, and U right here, and they remove the bottleneck. So instead of going to D in this way, right, directly like that, because we removed the incident, we're going to go back through the upper diagram. And that's going to give you back the solution we already know, right? One which you have the rarefaction fan here, but they all carry the same traffic state C. So what you see is actually the acceleration that you see here, okay? And then the same thing for C and D. You can draw a line right here, right? So you have traffic state C, traffic state D, and then you have to see if it's case 1 or 2. Okay, it turns out that it is case 2, right? Density in C is greater than density in D. So you keep going down the diagram like that as in case 2 solutions. But again, all the wave speeds right here are all equal to the free flow speed U. Okay, and that's, we're almost done. Finally, we have here two solutions, or two, this shock and this wave speed that cross right here. Okay, and then again, let's draw a line. Here you see state C, state A, okay? Right, so upstream is going to be less dense than downstream. So it's going to be a shock solution, right? The deceleration solution. But what happens is that A and C, let me clear out this section right here. It takes a while to. All right, so A and C are in the same line, right? So the interface is going to be the slope of that line. All right, so that is the incident example. And now from this solution, we can calculate a bunch of things. For example, so this is the same picture, but on a different format. For example, the maximum Q, you can see just graphically that it happens at T1 when the incident is removed, right? Because just by observing the picture, right? No math needed. And then, yeah, you could calculate this maximum Q just by, the geometry of the figure. All right? Another possible question is how far upstream the Q will spill back. Right? So this is how far upstream, right? Because at this point you have very little congestion, but you do have. So this is the point. And again, it's just intersecting these lines. Another typical thing we'd like to know is a typical trajectory. So we do it as always. All right, so here's the speed of A, here's the speed of U, and here's the speed of C. Right, and we already know how to compute the speed of vehicles inside a given traffic state. Okay, now there's a bunch of other questions related to delay, of course, right? So what is the total delay caused by this incident? Now, we could calculate it, and we're going to talk about it probably next time. It turns out that there's much better ways to doing the calculation of delays, and we're going to use n-curves, and that's chapter 3. Okay. Yeah, I would encourage you guys to please redo this example of the incident, but this time with a piecewise linear diagram. Okay? So piecewise linear, it's not a triangle, right? It has, I guess a triangle is a special case, but this one has 4 edges like that. Okay, so here you need to be careful with the discontinuity points right there. Okay? So, for example, when you're going from U to D, right? So after the incident has been removed, so you start from here, right, and you go creep up the fundamental diagram, right, in our case 2 solution. Then when you reach point B, up here, it means that at this point you're going to have all the wave speeds from W1 to W2 right here. All right, so that's why, let me try to zoom in here. Oops. No, I can't zoom in. It's okay. So that's why you have all the speeds here between W1 and W2 in state B. Okay, like that. So that's here, yeah, it's like we have a fan, but they all carry the same flow of state B. All right, and then you keep going up the diagram up to point C, and at C again you have all the wave speeds between W2 and U2 right here. So this is U2, the speed of that branch right there. All right, so here you have the second fan, but all those again carry the same flow of C. And finally, when you continue up to point D, which is right here, you pass by point E first, and again point E will have all the wave speeds between U2, which is the slope here, and U1. Okay, so now the fan, but is traffic state E. And finally, from E to D, which are next to each other, they're in the same line, so it's going to be a straight line slope U1 between E and D. All right, so please go over this on your own, please. It's a good example how to, get a hold rubber hit around case 2. Okay, what if, so here, if the bottleneck capacity changes from mu1 to mu2 in the middle there, and we're back to the triangle diagram. Okay, so for example, yeah, you have the first incident, and then here at this point, you know, maybe the hero unit came in and, you know, blocked another lane for a little while, so it causes the capacity to drop a little bit. Okay, and then they remove the whole incident. So the solution starts the same way, right, up to here. And then when the capacity changes, so you go from one capacity, which we call mu1 now, in this traffic states. So that's going to define D1 and U1. And then the same for the second capacity, D2 and U2, right? Okay, so when that happens, it's kind of you restart the problem, right? And you draw a line here and figure out all your Riemann problems. Okay, so first between, well, A and U1, we already figured that out. Then between U1 and U2, right? Now, they're, yeah, between U1 and U2 right here, they're in the same line, the same branch. So really, yeah, it's going to be a solution where, since they join by the same line, the interface is going to be the line of slope W, or negative W. Okay. Yeah, in general, when they're both traffic states are in the same regime in the triangular diagram, it doesn't matter really if it's case 1 or case 2, right? Because always the interface is the single line and the slope is given. The only time where you need to know if it's case 1 or case 2, and again, it's only for triangular diagrams here, it's when the traffic states are in different branches. Okay, so that's why from U1 to U2, it's just the same negative W line. All right, and then from U2 to D2, we already know it's a flat interface, right? Following the location of the incident. And then finally between D2 and D1, right here, right, they're in the same line again. So it's going to be a shock of speed U. Okay, and the same happens here, right? It's removed. We already know how to remove incidents. The only new point is right here where they cross. And before we had state A, but now, yeah, now we're going to have state U2 and A. So we're going to need another shock, right, from A to U2. And the speed right here, yeah, that's the notation, the speed between A and U2. Okay, that slope right there, which is a little steeper than the other one. That's why the Q grows a little faster from this point on. Okay, and then we already know how to compute this point again. And again, this is traffic state A. Okay, so if you wanted to draw a trajectory here, let's do a good one. All right, so these are the speed of vehicles, V1 and V2. So let me do one that crosses both. So probably this one, right? That's speed U. You put low rate in A. Then inside U1, you slow down a little bit. Say that's it. And then V2, you got to slow down even more. So let's say that's a V2. And then you keep going at frequency U. Wait, no, that's the slope. Okay? And again, we could answer all these questions, how far the Q reached upstream, etc., etc. All right. Now, notice that this happens always in traffic, right? Is this delay in which things happen. So, for example, here, you know, when the incident is removed, you don't find out about it at an upstream location only after the wave has passed, right? So there's a delay between things happen at the incident location and upstream, and that's the delay of the wave speed, right? For example, if you're observer right there, you would never guess that there was an incident, because if you're just observing here, nothing happened, okay? Or if you're here, you would see free flow and then you would see a congestion, but then it recovers. People call that sometimes phantom jam, right? Or ghost jam, because they don't see the incident happening. It might be way down the road. They only see the effects of it, okay? All right, and now let's do a moving bottleneck, which is really important. So it's pretty much the same setup as before, but instead of an incident, we have a slow vehicle. So it's a slow vehicle that will travel our freeway so from location x naught to x naught plus some length L. And it goes at a constant speed V. Okay? So here we're going to define the same flow of the capacity of the bottleneck, let's say. All right, so n minus 1. We're going to explain why, but the assumption here is that the bottleneck blocks one lane. The same as an incident, but it's like when you have a moving bottleneck, like a slow truck, it's like an incident that moves at a certain speed. So when you're downstream of the slow truck, right, you would see the same flow, or nearly, as if it was caused by an incident that is fixed, right? The downstream traffic state will be the same, and n minus 1 times q. Okay, then for QU, let's see the picture. All right, so this is we're going to call it the moving bottleneck line, right? The one that goes by state, we called it. All right, so here's a 2-lane highway, I guess, right? And then we have a slow truck in one of the lanes. So downstream of the truck, so this is the truck, just going at a straight speed. Downstream of the truck, state D, right, is going to be Q. The flow right there is going to be Q. And I was saying that downstream of the truck, you don't know if it was caused by a moving incident or a stationary incident, right? So, and that's the same state D as before. Okay, now it turns out that moving bottlenecks in the fundamental diagram are represented by a straight line with the slope given by the speed of this bottleneck. Okay, which is a nice generalization of the incident, right? Because the incident, you can see it now as a stationary bottleneck, where the speed is the slope of this line, which of course is 0, right? So moving bottlenecks are really a straightforward generalization, let's say, when you look at it this way. Okay, so really that's it, because then all the flows are defined in this similar way, all the interfaces, they're all the same. It's just that now state U is slightly higher than state U before, which was this one, remember? But all the logic is the same. So you should be able to understand now this diagram right here. And again, if you go compared to the other one, the only difference again is that in the other one, the speed here is 0. Okay? We're going to talk about moving bottlenecks in more detail, because they turn out to explain a lot of things when you consider that lane changes could be moving bottlenecks, or trucks on uphill grades, etc. Okay, so we're going to examine more in detail what happens with state D and what it represents in the case of these bottlenecks. very good. Let me check my time. Yeah, I have maybe 3 minutes left. Okay, when you have moving bottlenecks, something curious happens is that the back of the queue, which we're used to it traveling upstream, can sometimes travel downstream, and it depends on the ambient traffic state. By ambient, I mean traffic state A, I guess. Right? So the state that you start with. All right, so see here, so this is the, we're going to call it capacity line of the moving bottleneck, right? So this line with slope V, this line we call it capacity line of the moving bottleneck. The reason we do that is because it's not clear whether D or U should be the capacity of the system with moving bottlenecks. So there's a debate. Some people argue it's D, some people argue it's U. So to make everybody happy, we just say that moving bottlenecks have this capacity line. Right, so once you have the line, you have states D and U, and that's going to define these 3 regions, and it depends where the input traffic A is. It's going to give you the slope, right, of the shock between U and A right here. So the shock AU. So this shock could go forward, as you see in the picture, and it's because the state A is in this region, right, between the flow of D and the flow of U, right, because this point is the flow of D and this point is the flow of U. So when A is in the middle, then you're going to have this back of the queue that travels forward or downstream, which is unusual. But you might have seen it in the real world, right? Like a queue of vehicles following a slow truck. Right, when you have more demand, so if traffic is way up here, of course you're going to have now a negative shock. So this is going to go all the way over here, right? So that's more usual. And finally, when the flow is here, if A were here, then nothing happens, right? Because QA is less than QD, so everybody can make it past the bottleneck. There's enough capacity in the remaining lanes that's not going to cause any disturbance. Okay, and then let's finish with piecewise trajectories. This is like a zoom up version. Now we're saying that the bottleneck, the moving bottleneck, accelerates, but accelerates in this way. So here we have 3. And let's assume point D is the same for all. That's capacity C. And then here you would have upstream state 1, upstream state 2, upstream state 3, corresponding to these 3 speeds, V1, V2, V3, right, of the bottleneck. So that's V1, V2, right, that's the trajectory of the bottleneck. V3, hope you can see that, V1, V2, V3. And those speeds will define the traffic states U1, U2, and U3, which are the ones here. Okay? Now, traffic state D is right here. Now, we say it's different than a void for reasons that will become clear next time. But, so please take a moment to understand this solution. And all these wave speeds are negative W, right? The wave speed, okay? Okay, so we're gonna leave it there, and I'll see you in class tomorrow.